We're given a quadrilateral, and one of its diagonals splits it into two parts. This triangle has an area S1 and this triangle has an area S2. The question is, can we find the ratio of the areas S1 divided by S2 by just using lengths of segments we have on the picture? And the answer is yes, we can. And now we're going to see how. Suppose the length of this segment is A and the length of this segment is B. Then it turns out that the ratio of the areas of S1 divided by S2 equals A divided by B. Let's drop the altitudes from this vertex to the diagonal and from this vertex to the diagonal. Suppose the diagonal has length d, and the altitudes from here and from here have lengths h1 and h2. Then s1, which is this area, equals the base d times the height h1 divided by 2. It's given here. And the area s2, which is this triangle, is given by d times h2 divided by 2. So it's here. And now we can divide these two equalities, and we get that S1 divided by S2 equals H1 divided by H2, because the D cancelled out and the 2's cancelled out. But we needed to prove that S1 divided by S2 is A over B, and we got that it's H1 over H2. So now we need to prove that H1 over H2 equals A over B. But take a look at these triangles. This triangle here and this triangle here. They're similar because they have a right angle here, and this angle here is the same because this is a straight line and this is a straight line. Now, due to this similarity, we can say that the ratio of the corresponding sides in the two triangles is equal. So h1 divided by h2 equals a divided by b. And so we're done. Now imagine we had the opposite situation in which we know that the ratio of the two areas is a divided by b, but we didn't know the ratio of the lengths of these segments. Would we be able to find that the ratio is necessarily a divided by b? Oh yes, because by writing the formulas for S1 and S2 again, we're going to get that S1 divided by S2 equals H1 divided by H2. And now these triangles are still similar, and therefore H1 divided by H2 would be the length of this segment divided by the length of this segment. And therefore, the ratio of the two lengths would be A over B. Now suppose that the quadrilateral is not convex. For example, if it is this quadrilateral we have. In this quadrilateral, one of the angles is more than 180 degrees, and that's why we call it non-convex. This is the diagonal with which we split the quadrilateral into two triangles, and you can see the shaded areas here and here are denoted by S2 and S1. And the goal here is to prove that the ratio S1 divided by S2 equals the ratio of these two segments, A divided by B. First of all, I'm going to mark this area as S3 and this area as S4. First of all, we know that the ratio S3 divided by S4 equals A divided by B. And what's more, from this triangle, we know that the area of S1 plus S3 divided by the area of S2 plus S4 equals A divided by B again. From the first equality, we get that S3 times B equals S4 times A. From the second equality, we get that S1 times B plus S3 times B equals S2 times A plus S4 times A. Now we subtract this equality from this equality, and then S3 times B cancels out and S4 times A cancels out, and then we get S1 times B equals S2 times A, from which it follows that S1 divided by S2 equals A divided by B. And this proof also works the other way around. Suppose that we wanted to find what's the ratio between this segment and this segment, then the only thing we need to do is to find the ratio of the areas of these triangles, and then we just take the ratio and apply it to these sides because it's the same ratio. A way you could prove that is to drop perpendiculars from this point to the dashed line here. So one of the perpendiculars will go maybe this way and the other one will go this way. Then the area of S1 would be d times the height h1 divided by 2, and the area of S2 would be d times the height h2 divided by 2. And so the ratio of the two areas would be exactly h1 divided by h2. And now this triangle here, the small triangle, would be similar to this triangle. And so the ratio of the red side to the blue side equals the ratio of the heights, which equals the ratio of the areas. Here's the optional problem. We have a quadrilateral, and we chose a point on this side of the quadrilateral such that it splits this side into two parts. This part has length A and this part has length B. Now consider the following three triangles. All of them have base this side of the quadrilateral. One of them has the third vertex here, the second has the third vertex here, and the third has the third vertex here. So this would be the first triangle, this would be the second triangle, and this would be the third triangle. They have areas S1, S2, and X3 respectively, and we need to prove this equation that S1 equals A divided by A plus B times S3 plus B divided by B plus A times S2. And here's the solution. I labeled the points on the picture as shown. Let S be the area of the whole quadrilateral. We'll put it here. And then we can split this area using the segments AE and EB into three areas. Area of ABE, which is S1, area of AED, which is here, and area of BEC, which is here. Now we know that the area of AED divided by the area of AEC equals the ratio between these two segments, A and B, so A divided by B. And therefore, the ratio of the areas of AED and ACD would be the ratio A divided by A plus B, because triangle AED has a base A, and triangle ACD has a base A plus B, and both have the same height here. So instead of writing area of AED, we can write A divided by A plus B times the area of ACD. And we can apply similar reasoning for the area of triangle BEC. We know that the area of BEC divided by the area of BED equals B divided by A. And therefore, the area of BEC divided by the area of BDC would be B divided by A plus B, because the first triangle has a base B, the second triangle has a base A plus B, and both triangles have the same height here. So we write area of BEC as B divided by A plus B times area of BCD. Notice that the area of ACD equals S, the area of the whole quadrilateral, minus the area of ABC. So we can write area of ACD as S minus S ABC. And then the area of BCD, notice that it equals the whole area S minus the area of triangle ABD. So we can write S of BCD as S minus S of ABD. But the area of ABC, this is exactly S3, and the area of ABD, this is exactly S2. And so we can rewrite this equation as follows. The coefficient in front of S, we have A divided by A plus B here, and B divided by A plus B here. So we get the sum of them here. And then minus A divided by A plus B times S3, which is here, and B divided by A plus B times S2, which is here. But now notice that we can cancel out the s's, because this s equals this s up there. Indeed, in this parenthesis, the expression equals 1. And here we have 1 times s, and here we have 1 times s, so we can cancel them. And what's left is 0 equals s1 minus A divided by A plus B s3 minus B divided by A plus B s2. So this is exactly what we needed to prove.